Okay, in 27, the first thing I'm meant to do is find a point at which two lines intersect, if indeed they do intersect. So let me go through how I think about that. Two lines that are the ranges of these two functions from the real numbers to R3. Notice that I've used a different independent variable t and s for both of them. Even if they were given to me as both t's, I would change one to s and the other to t. For the following reason: these things intersect if there's an ordered pair of numbers that, when substituted for s and t respectively, makes the expressions equal. That is to say, now imagine that you're out here in 3 space and you've got two lines, one that goes like that and another that goes like that. Perhaps one of them, this is the point here that might correspond to t is 1. And then on the other blue one over here, this right here might be where s is equal to 1. Okay, that is to say, these things intersect, but when the independent variable for the function is the same value, that's not the point of intersection. So perhaps they meet over here where s is 5 while t is 7. I don't know. We'll find out what it particularly is, but this is just arguing that this is a possibility, that the independent variable has a different value for this function and this function at the point of intersection. So let's figure out what s and t probably what they are. So that that ordered pair s and t will be a solution to the system 2t plus 1 is s plus 2. That's equating the first components. Here I started equating the second components and I made a typo, so please excuse the ugliness. And then the third components also are equated. Now I want to find an implication of this system of equations. What I'm going to do is I'm going to subtract what I will call 2 times the first equation from the second. So 4t minus 2 times 2t will give me 0t. And 3 minus 2 times 1, so you can keep track of what I'm doing. Maybe I'll label these things 1, maybe A, B, and C. And what I'm going to do is, just so that you can understand what I'm thinking of C minus 2 times A. Okay. So looking at C, 4t plus 3 is equal to, etc. And I take 4t minus 2 times 2t, 3 minus 2 times 1. Let's see, that leaves me with a 1 is equal to, and negative 4 minus 2 times s is negative 6s, while negative 1 minus 2 times 2 is negative 5. Okay, so that was one way of combining these equations. I combined C and A, and certainly I should have a system of 3 equations here, but just in my head I'm going to say I'll have a system of 3 equations here, maybe 3. But first of all, I want to simply rearrange this equation to isolate s. And let's see what would happen. If I add 5 to both sides, I'd get negative 6s is equal to 1 plus 5 is 6. So I would get s is 6 divided by negative 6. That's negative 1. Hey, you know what? That is all I need. Presumably, these lines really do intersect. And they intersect at the point that is described by putting 1 in for s here. Okay, so let me see if that works out. Be a solution to this system of true. All solutions should be of the form negative 1. Well, look, if s needs to be negative 1, then I can put this back, this number, negative 1, back into, say, that first equation right there. Just say that 2t plus 1 is negative 1 plus 2. Okay, so for that would mean that 2t is negative 1 plus 2, that is a 1, and I subtract 1 from both sides and get a 0. When t is 0. Alright, let me think for a second. When t is 0, this expression is 1, 2, 3. When s is negative 1, this is 1, 2, negative 4 times negative 1 is positive 4, minus 1 is 3. Perfect. Okay, so I didn't have to do a whole lot of work. I didn't have to write a bunch of equations here, right? So this and this implies that. Okay. Now, the idea is this is a system of equations, and this is a maximally simplified version of the system of equations. And so the solution, let's see, the only solution to this system is a solution to that. Let's see. Let's make sure I get the order right. S and then t, so negative 1 and then 0. Alright, so the lines intersect at, and this, I put in t for 0 up there, and I get the point 1, 2, 3. Now I need to describe the plane that contains these two lines. Let me see. The plane. There should be a new paragraph, but put that in isolation right there. The plane that contains these lines is the solution set to, okay, so I need the normal vector dotted with an arbitrary point on there. The normal vector is going to be the cross product of the direction of the first line and the direction of the second line. So 2, 3, 4, that's the direction of the first line. Cross product with the direction of the second line, that is 1, 2, negative 4. And the cross product, that will give me the normal vector. I am meant to then, let's put that in parentheses, dot that with an arbitrary point on there, x, y, z. And I will get the same thing no matter what point I put in there, so I'm tempted to write is equal to the dot product of that cross product with a particular point, say this point 1, 2, 3, that is on the plane. But instead, let me conserve some room by putting in some parentheses and writing minus 1, 2, 3. Alright, that equal to 0. See, that would say that the dot product of this cross product with that is equal to the dot product of the cross product with that, just by some algebraic rearrangement, but that indeed is the algebraic equation. It can be fleshed out a bit, if you like, by calculating explicitly the cross product and calculating explicitly the dot product, but this is all I need. Nice expert level presentation. I'm already at problem 27, so I'm an expert, and you are too.